to you. So today we're very fortunate to have as our speaker Thomas Schoen. He's an associate professor at the Division of Automatic Control at Linköping University in Sweden. Received his PhD degree in automatic control in February of 2006, master's degree in applied physics and electrical engineering, and a bachelor's degree in business administration economics in 2001. He's held various visiting positions at the University of Cambridge, University of Newcastle in Australia. He's a senior member of the IEEE, and he received the Best Teacher Award at the Institute of Technology in Linköping University in 2009. Congratulations. His main research interests are in nonlinear inference problems, especially within the context of dynamical systems, solved using probabilistic methods. He is active within the fields of machine learning, signal processing, and automatic control. He pursues both basic interests and applied research, where the latter is typically carried out in collaboration with industry. So, without further ado, welcome. Thank you.
Thank you. Thanks a lot. Is the sound working?
Yes.
Yep, good. Thanks a lot for the invitation. Very glad to be here. Nice to see a big crowd. So what I'll be talking about today is sensor fusion using world models, as I call it. So I'll explain a bit more what I mean by that. So I've given a couple of seminars here over the last month or two, so there will inevitably be a bit of an overlap in between those, but there should be a fair amount of new material in this one. Right, so I'll start by an introductory example that I have together with a company called Xsense to provide inertial sensors. So the context here is motion capture. So if you want to figure out the motions I'm doing at the moment and you want to record them. So what you could do, you could use a camera-based system, or you could equip yourself with a little suit like that, which has 17 of these integrated, which is an IMU, so an inertial measurement unit. And in that you have accelerometers, gyroscopes, magnetometers measuring the specific force and the angular velocity and the magnetic field. And then you integrate all of these. So that's 9 by 17 measurements coming in, and you need to fuse them together in real time and output the position and orientation of this human body. So how can you do that? Well, if you start and try simple things first, as you should always do, and only make use of the inertial information. So we're not using any more elaborate models. So I use this as a tool to show you that models are quite useful. And it's going to be a very simple world model in this example. I'll give you a few more interesting examples later on. So this is what happens if you, well, it's actually not what happened to this person, but this is what happens if I just use the inertial information and just try to do my best at figuring out what happens. And again, let's see how we can do this better, because we have quite a lot of knowledge of this system. But in fact, you're all this system. I mean, you have a body, so you know that your hand is attached to your arm, there's an elbow and an upper arm and so on and so forth. So let's use that. So we make use of a biomechanical model, just explaining that, and see what happens. So we now have the inertial sensors and biomechanical model. Okay, so starts moving around. At least he's not exploding, so that is good. However, he is sinking through the ground, so that is still a problem. And why is that happening? Well, the inertial sensor is a relative sensor. It gives you no absolute information whatsoever. And these are, as was discussed earlier, they cost a bit, but they are still considered cheap if you compare to military-grade sensors. So that means they will drift pretty quickly, as you just saw. So how can we fix that? Well, we know that I'm walking on a floor here, so I will probably not sink through to the other floor. So let's include that in our model as well. So that serves as a very simple first world model. It's just a flat ground. So we do that by detecting when you have, because when you're walking right there's zero velocity. Well, that's a lot of information that can be used. So we use that together with the world model, and now it's looking better when it's moving around. You don't see the absolute position here. So this is actually not perfect either. I mean, to your eye, this looks beautiful because that's probably what happens. But the position will still drift off on the surface here. So we can fix that as well by adding adding another sensor, so we add ultra-wideband in this case, which is radio technology that you can use for indoor positioning. So we use that and add to get position. And now I show a little experiment here where you get fairly accurate indoor positioning as well. So what you see is the real-time estimate of this person in terms of position and orientation. That's obviously the skeleton here as he's moving around. And it stays pretty fixed to the true position, which you see from the person, of course. Deviates a bit here and there, but does a decent job. Why does it deviate? Well, if I only take that sensor unit, which has an IMU and the ultra-wideband in it, then the quality will be within centimeter accuracy in terms of the positioning in a room like this. And the orientation will be sub-degree in all three directions. But still you can see that the error here is clearly larger than a few centimeters. That's because you only have one ultra-wideband transmitter attached to this person.
Is the IMUs and gyros more than one of them distributed across the body or just one place?
So the IMU, you have 17 IMUs. So you have your symmetrics, you have on each side and one on your head. And the ultra-wideband can only sit on one place because we only used one here. So that means we can still drift off a bit. If I place it here, my upper body can drift off and so on.
So the ultra-wideband is not 3D, right? It's single link?
Single link, yes. But over time, it becomes 3D because I got a dynamical model here as well. So when I'm walking around, I'm receiving multiple measurements and then I triangulate, implicitly triangulate, and I can get an estimate, yeah.
Do you have also models of the motion of the person?
Yes.
So there's multiple ultra-wideband transmitters in the room?
Yes, you can see them here. It's black,
Okay.
and then they go crazy. Yeah.
Okay.
And as you saw here in the, as we were speaking, which if you compare with vision system, you can't do this if you put a box over the person. With a vision system, that's going to be hard, whereas you can still see exactly what he's doing in there. Okay, so that was just to get started to show what type of problems we're talking about in a very simple setting here. So what's this? This is what I refer to as sensor fusion. So that means you have multiple data coming in. Here, I mean, it's not too much, but still a fair bit. You have 17 units, each reporting 9 signals, 17 times 9. That's coming in at, so the inertial sensor is coming at 200 hertz here, I think. So it's a fair data stream that comes in that you need to do something clever with. And then you need a systematic way of processing that. So what I showed you here, I hope I showed you that making use of models for doing this makes lots of sense, as you all know. So again, sensor fusion, what trying to define that, I'll say it's the process of using information from several different sensors to find out what's going on. That typically means, as you saw, dynamical states, so things that change over time, but also possibly static parameters that might be there. So again, you have a bunch of sensors and you have a world model. The world model we use here was very simple. I'll show you some more interesting ones soon. You need a dynamical model explaining what's happening, the dynamics of the thing. You need a sensor model that explains how the sensor measurements talks to the dynamical model, how your measurements are related to the state. Once you have all that, then you have a bigger or smaller inference problem that you need to solve. So you need an inference algorithm as well. And on top of that, you have what's not shown here, which I refer to as the supporting infrastructure, lacking a better word for it, which is all the bits and pieces that you have to do in order to do what you really want to do. So like time synchronization and calibration and all these things that takes time. That's important to also remember that. Then you hand out some form of situational awareness that you then give to your customer, whatever your customer is. It could be a control system, for example, or in this case, the movie industry is using this, for example. They are happy with just getting the estimate, and then you can overlay Gollum or whoever you want to overlay. And this, of course, just one example leads to many different questions, such as can you incorporate more sensors? How do you make use of more informative world models? As you know, we're getting better and better world models as we speak now. So how can we use that? How can we solve the inherent inference problem that we're dealing with? It's a pretty tricky one, actually, in the general case. And quite importantly, can you do this systematically so you don't have to redo the thing all the time? Can you do this on an industrial scale, so to speak?
So before you go on, you may be addressing this, but as for this world model, it seems like this could be a difficult problem because, if it's a spongy floor, for instance, versus a hard concrete floor, is that something you think you could derive automatically from what you're observing? Is it something that comes from a database, or what's the view on that?
That could absolutely come from a database, for example. So I'll show you a bit on fighter aircraft navigation. They use a system like this to navigate. And then you can incorporate, for example, are you flying over terrain which involves lots of vegetation, or is it sea, or is it concrete for that matter? So like you said. And then you can use that in your algorithm.
So if you had Google Street View of the complete world, or annotated,
yep.
based on where you are, you could adjust the world view, the world model.
Yes,
right?
yes, yeah, yeah. And quite a lot can be done systematically, I would say. So, and it boils down to these 5 areas, as I view it, based on my experience with the examples I've been involved in. So, you need probabilistic models, or I prefer to use probabilistic models of dynamical systems, because why do I do that? Well, there is uncertainty inherent in any measurement you receive. There is uncertainty in whatever model. We know one thing about models, as someone said, is that it's wrong, but hopefully it's helpful, right? So that means there's lots of uncertainty in the model as well. So how do you get a handle on that? Well, there's an entire field of probability theory that gives us the tools, so let's just use that. We don't have to reinvent that. They provide us with a nice way of capturing, working, and representing with uncertainty. So that's why I'm using probabilistic models. Then you need to work out the sensor models. Typically involves a fair bit of knowledge about the sensor itself, if it's a camera or a radio or what have you. I mean, we used to organize, we still do to some extent, the academic world into different sensors. You have camera, that's computer vision, and you have radar, that's the radar guys, and so on. But when you think about sensor fusion, you can't really work like that. You need to talk to everyone, and you need to integrate everything. Extremely important, extremely hard, because we're only human. And then you have the world models that are coming, again, as we just discussed, they're becoming more and more available. But just with simple stuff, we can actually do quite interesting things. Then you need to formulate and solve an inference problem, which will be nonlinear, and it's going to be non-Gaussian. So you typically can't use Kalman filters. For some applications you can, but not when you're using more complex world models. It's going to be hard, at least. So you need something else. And then the surrounding infrastructure, which is all the things that you forget, but that you realize that you have to solve when you start doing it. And they should be respected as well. So that's what I would refer to as sensor fusion, dealing with this. All right, so the story I'm trying to tell here is, again, we're dealing with dynamical systems, so we need dynamical models. These dynamical systems, they exist in a world, so we need a model of the world. It can be very simple, as you just saw, just a floor, and it can be more involved. But we need something at least.
Would the world not be dynamic as well?
Absolutely. The world, yeah. Where do you draw the boundary? I mean, you're all sitting here pretty statically, so for me, you're part of the world, so to speak, because you're not moving too much. Whereas, depends on the application. Absolutely. What is a dynamical object, and what is the world? And it's also interesting to there's a whole bunch of research going on in SLAM, as you probably see, simultaneous localization and mapping, where you say, I don't know the world, so I need to find the world model as well. Yeah, absolutely. But you still need some representation of it, though. Yeah. And then you have your sensors, and you make use of these sensors to perceive your motion or someone else's motion, or maybe both. So you need to integrate these. And you need to be able to solve the resulting inference problem to figure out what's happening here. So this is what I'll try to talk to you about today. So in terms of an outline, I'll talk a bit start with some background on sensor fusion. So I've given you something to have in the back of your mind for the rest of the talk in terms of this example. I'll talk a bit about probabilistic models for dynamical systems. State inference using the particle filter, that's a filter I tend to use a fair bit for solving these systems. And then I'll say a few words about the Rao-Blackwellized particle filter to throw in some new technical stuff into this talk, which is a very useful technique. And then I'll talk about how do you incorporate world models that are more interesting than just the floor into these inference problems. And then I'll give you a few industrial application examples that I've been involved with. So fighter aircraft navigation, automotive localization, indoor localization, underwater localization. So if you like, you go up from the sky, you do the fighter stuff up there. On the floor, indoors, we have people moving out indoors. And you go out on the street, you have the cars, and you go underwater, and we have the underwater stuff down there. And then towards the end, I'll give you a concluding experiment just to widen the scope a bit, and then conclude. Okay, so how do you, so for those of you who, I gave a tutorial on particle filters yesterday, so I'm sorry for the repeating myself for you guys. The basic representation is two discrete time stochastic processes that I use to model the dynamical system. So we got this process X, the blue, which is representing the state of the system. So position, orientation, velocity, acceleration, etc. And then you have a measurement process Y, that's your measurement stream from your sensors. And then we use a nonlinear, non-Gaussian model to describe this. And the way we describe it, it's a Markov model. So the state at time t plus 1, given the state at time t, is distributed according to some distribution f, possibly parameterized by some unknown static parameters, theta, the red bits. Possibly you have some known input as well. Today we'll focus on the blue bits here. I won't worry about the red bits. That's an extremely interesting problem as well, but that's another talk. And then the other model is the measurement model. Again, another distribution G that tells you what is the measurement, how is the measurement distributed condition on the state. So that's the model we're going to use. So that means when I talk about the model, I'm talking about the probability density function. That's what I mean by a model. This is referred to as state space model, hidden Markov model, latent Markov model, depending on where you come from. Okay, so that's the model. What's the aim? What we're trying to do? Well, we're trying to obtain a probabilistic representation of the knowledge that we have about the state based on the measurements that we're receiving. So that means a point estimate is not going to be good enough. We cannot rely on that. I will show you why soon. That's dangerous. So you need something a bit wider, a wider representation. So one good idea is to use a distribution as well. So looking at what I call the filtering PDF. So that is the distribution of the state given all the measurements up to time t. So based on everything I've seen, what is the distribution of the state? Then from that, you can then extract, if you want, a point estimate or compute confidence intervals and do all the things you might want. But that's the object we're trying to capture. The obvious question is now, how do you compute this object? How do you find this? So I'll just derive the equations you need to solve and then see how to find it. So we're looking for this object. That means using Bayes' theorem, I can split this into working with the distribution of the measurement given the state and the one step ahead predictor. And then we recognize using Markov property that this is actually the model coming in here. That's our measurement model. The distribution for that comes in there. And this is just the one step ahead predictor. So very, very simple. And this gives us part of the recursions, because what does this tell us? It tells us if we have this, then just make use of your model and you have the filtering PDF. So very simple. So what about the prediction PDF? How do you find that? Well, just marginalize. So look at the joint distribution of x at time t and x at time t minus 1. Just integrate out x at time t minus 1. And again, just using conditional probabilities and the Markov property, what do you get? You get the dynamics comes in here and the filtering distribution you had yesterday, which intuitively is correct, because what you're trying to do is to predict one step into the future. And what information do you have at your disposal? Well, you have the filtering distribution, the best estimate you produced yesterday, and you have the dynamics that tells you what's probably going to happen in the future. So it's natural that these objects pop up here. And then we insert these into the integral, and that's what we end up with. Okay? So extremely simple to derive these equations. But that's sort of where the simple bit stops, because now we need to solve these, and that's hard. Because if you look at this, for example, integrating over the states, let's say it's dimension 30, so you got 30 integrals, and the thing in here does not allow for an analytical solution. So what do you do about that? That's the hard bit that we're going to talk about. So this was just summarizing what we just showed, and this is typically referred to as the measurement update, and that's the time update or prediction. Okay, so just to remind you, as always, you should always fall back and solve the linear case, because that is simple and everything is closed form, even though there are no such system in the real world, more or less. But it's good to make sure that you're doing the right thing. So for the LGSS model, so linear Gaussian state space model, most of you know that the solution to these equations will be given by the Kalman filter. So just take that model, insert that into these two equations, use basic properties of multivariable Gaussians, and you have the Kalman filter popping out. So that's reassuring. That's what you want to be happening. Okay, the question is, what obvious question is, what do you do in an interesting case? That's when it's not linear, not Gaussian, because then there is no closed form solution anymore. So
what is it that's not linear in this case?
What is not, so the function f here, so that is a distribution. Mm-hmm. So another way of explaining the same model is to say xt plus 1 is equal to some nonlinear function f bar of xt and ut, and you add some process noise. So this is the way you typically see the systems described in engineering literature. I'm a control engineer, so this is typically how I'm taught to view this. But then doing the mathematics that I want to do, that is a much more convenient representation. So that's why I prefer to talk about that. But here you see where the nonlinearity enters, and the same for the measurement equation.
So you're talking about x of t plus 1 being linearly related to x of t and u of t.
Exactly, that's what I mean when I talk about.
Okay, so it's f that you're talking about. Okay.
Yes.
All right.
Yep. Good.
Okay.
Yeah. Exactly. So here the function f bar is just a linear transformation. Yeah. And that's also intuitive that is what happens, because a linear transformation of a Gaussian variable, that must be Gaussian. You can't transform yourself out of that. So everything that you talk about when it comes to a linear system, it will be Gaussian, hence simple. But then, okay, so what do you do when we have a nonlinear model, and you also have a world model, including a map? So how does the map fit into this picture? So think a bit about that. I'll explain in a second. So first of all, we need some form of general representation of the filtering PDF. So I cannot assume any specific functional form of it. Or at least I don't want to do that, because that's going to be wrong, and I don't want to do that. There are very interesting theory based on doing that. I use that a lot as well. But let's try another way of solving it. And then once we have that, we need to try and solve these equations as good as possible. So that's the task. Okay, so I'm using something referred to as the particle filter, or a sequential Monte Carlo method to do this. So I gave a tutorial yesterday on this, so I'm not going to spend too much time on this, but I'll just give you the key idea in case you haven't seen it before. How many of you have seen particle filters before? So So a few, not too many. Good. Then I'll spend some time on this. Okay. So what is the particle filter? It's a nonlinear filter that allows you to find this filtering distribution as accurately as you want, more or less. So what does it do? It computes the filter for the model that we've just introduced, and it maintains an empirical distribution of this form. So, and for intuition, you can think of each so-called particle as one simulation of the system. And then you only keep the good ones. So this is a hand-wavy, but it's good for intuition to think of it like this. And capital N here is typically pretty high, so you have quite a few ideas about what's going on. So that's a representation. This I should probably explain. So delta, think of that just as a point mass. So that means I have a bunch of samples, and so here we have capital N equals to 3, and this is xi, x1, x2, x3, and so on. So it's just a point mass, and each particle then has a weight associated to it as well, providing information about, in loosely speaking, how good is this particular simulation at solving this. Okay, and this approximation, so that all sounded a bit ad hoc, and it's not. This will converge to the true solution. So if you're interested, we sorted that out in a paper, and it converges asymptotically. So as the number of particles, capital N, tends to infinity. Okay, so these weights and the particles, we can then use them to solve these integrals. And the way the way we do that is we just insert our approximation into the integral, and these Diracs, which is a generalized function that works together with the integral and evaluates the test function, which is just the state here. And you have a way of computing your estimates, just to give you an example of that. So the underlying theory, so this was just 2 slides, just giving a brief, hopefully a small idea about what's going on here. The underlying theory has been developed for 20 years, pretty much exactly 20 years. So if you're interested in that, there's a nice tutorial there. I've also got a PhD course covering this if you're interested in it in more detail. Okay, let's make this a bit more concrete and show what happens. So this is a little toy problem that we can use to see how this works. So I'm considering a one-dimensional localization example where we live in one dimension, and using a simple dynamical model which just tells you that the position tomorrow is the position we have today, plus the velocity which we measure, plus some random disturbance that we don't know. And then we measure the position via some nonlinear transformation h, disturbed by some noise. And the setting is the following. So think of this as an aircraft flying up there around 90 meters, plus or minus a bit. And this is the ground. So this is now the world model that you have, which is the height profile from a terrain database. And then from the beginning here, you use, in terms of an aircraft, you use a radar to measure the distance down to ground. So that's going to be 60. That's going to be the report from the first measurement. And then you have your world model, and then you look into your world model and you see, so where is it 60 meters from where I am, so to speak. And then, as you see by the dashed line there are a few places where that can happen. So we then use the particle filter to represent this, and after one measurement, this is the representation I obtain for the filtering distribution. And as you can see, it's a multimodal distribution, which again is what you would expect, because based on that measurement, I have no idea where I am. I mean, it's just as probably that I'm there, and so on and so forth. And that's straightforward. That's not a problem at all. We just capture that, and we represent that, and we acknowledge the uncertainty that we have, as you see. So again, here is what I mean by the danger in extracting a point estimate. So if you insist on receiving one estimate, a scalar value where you are, how do you get, you can't get that reliably from there. So there's no point in even trying. But from this representation, you can at least you can see what goes on, and you make your decisions based on that. And that's going to be much better. Okay, let's see what happens when we go wrong. So this was the situation after 1 measurement. And then after 3 measurements, we're already a bit more certain about where we are, because then you have seen more and more information, and you map that to your world model, which is exactly what you do when you're finding your way in a new city, so to speak. So after you moved around a bit, you gather more information. The same happens for us here. And you can see intuitively it's correct that we have a fair bit of probability there and there, because if you look at the world models, they are pretty similar at these points in times. But they will start change after a while. So after 10 measurements, you know pretty much where you are. So that's the idea. So this was the most simple example I could think of to illustrate the idea. It shows you a few things. For example, this is clearly a multimodal filtering distribution, as I've said many times now. And it's straightforward to represent and work with that using a particle filter. It would be horrible to work with this using, for example, an extended Kalman filter or something like that. Because then you need a software swamp, I would call it, with lots of if, then, else things that's not maintainable. So it also highlights some of the key capabilities of the particle filter, which is automatically handles an unknown number of different hypotheses that you might have. And these numbers might change over time dynamically, that's fine. And you can work with nonlinear, non-Gaussian models. And this we've implemented in this fighter. Saab, together with Saab, we actually build this, well, not we, but Saab built this in Linköping. So we've implemented this to solve the navigation problem in the fighter aircraft. And that we did, that was pretty much when I started as a PhD student, so that was 10 years ago now, a bit less. And back then, that's quite some time ago. And if you know something about these, is that the computers that sit in there, they are not the newest ones, because you have security issues and all sorts of things. But it still worked. Back then, it worked on board on those computers.
What was the dimension of the problem?
So then we looked at, so the state dimension is high, but the number of around 30, let's say that. But the number of states that enters into the database lookup is small. It's just 2 dimensions. So I'm using a particle filter for that lateral and longitudinal position. These are the only ones that need to go into the database query. So that's why I use a particle filter only in those 2 dimensions, and then I use Kalman filters for the rest. So I'll talk a bit more about how to do that soon. So that's a way of harnessing the cursor dimensionality here, if you like. Because the downside of the particle filter is that this is going to cost. This is going to be much more expensive than updating a Gaussian, of course.
And how did you decide which 2 states you should? Because you had a suspicion they were not linear or Gaussian.
No, that is simple. I'd look at the map, because the map is the most nonlinear thing here. So the map that's used in this is a terrain database of the operational area. And you use inertial sensors together with this terrain database. That's how these things work, or a few of them at least. And then you think about the map. So what do I need to work with a map? And that's the position. You don't need velocities or orientations or things like that to go in there. Not directly anyway. So that's how we choose. And what happens from so this is 1 dimension, and this is now 2 dimensions. And you can start adding more and more dimensions and making it more and more interesting, I guess. So your question is perfect. That brings me into this Rao-Blackwellized particle filter. What is that? That's if a general, whenever you solve a problem, if your problem has a structure, you should of course exploit that and use that structure, because that is there for you to use whenever you construct an algorithm. Then you'll probably end up with a better solution. And what this Rao-Blackwellized particle filter does is that it exploits a conditionally linear Gaussian substructure. That means based on some of the states, the rest of the states will obey a linear Gaussian model. So let me explain that in some more detail. So we divide the state into a red part and a blue part. Red is dangerous, so that's the nonlinear part. The blue part is simple, that's the linear part. Okay? And if we formally define this model class, it's a class where you can partition your state into these red and blue bits. And the conditional process of for the linear state conditioned on all the previous nonlinear states, that process will then be linear Gaussian. So then it does not make sense to use the particle filter for those states. We can just use a Kalman filter, possibly. Let's be a bit more concrete than that and have a look at what this model looks like. So if you prefer equations, look on the left-hand side, and if you like graphical models, look here. So this is what the model looks like. So again, color-coded the equation so you can see more easy what we're dealing with. So again, if I give you the red bits, what are you left with? Then you're left with a linear Gaussian model. Well, I should have said that I assume the distribution of the noise is to be Gaussian. But if someone gives you the red bits, you have a simple problem. Of course, that's something that we must be able to exploit somehow. It's not going to be straightforward to divide this and run a Kalman filter here and a particle filter here. Why? Well, that you can realize by looking at this, because it's messed up, if you like. It's mixed. You have dependencies all over the place. So you need to think a bit about exactly how to link the Kalman and the particle filter. But that can be done. So, and what happens when you do this? So I'm not going into the details here. I'll give you a reference to a paper if you want to have a look at it. What you can also prove is that you will end up with better estimates, where better in the sense of a lower variance by doing this. Again, also intuitively correct, I think, because we are using the Kalman filter for a linear Gaussian substructure, and there is nothing better you can do for a linear Gaussian substructure. So it makes sense that we can obtain a better estimate. And this, again, coming back to your question, this gives us access to more challenging models. For example, high-dimensional models. And to show you what the structure looks like, we can split this distribution that we're looking for into two parts. Technical detail here that some of you are thinking about now is that I use 1 to t here. That's because I have to, because I need to condition on the entire nonlinear state trajectory, otherwise it won't work. So that's what I have to do, but that's okay. And then we target this density using a Kalman filter with closed form expressions, and we just let the particle filter work on this one. And what that gives us is that, again, we get an empirical estimate from the particle filter, and you get conditional Kalman filters for each, so one individual Kalman filter per particle. That provides you just normal distributions for the other density. Combining them, you get a weighted sum of Gaussians. So this is now the representation that we're working with. So each particle has one Kalman filter attached to it. And then it's also, some of you are thinking, so what about computational complexity if you're running, let's say, 10,000 particles here? And that means this is a covariance matrix, which maybe that's dimension 20 by 20, let's say, and you need to invert those. So of course, that can end up being computationally costly. But there are also quite a lot of interesting model structures where you end up being able to use the same covariance for all particles. And then all of a sudden you have something that's actually computationally cheaper. Again, if you prefer pictures, this is what it looks like in 2D. That's all I can plot. So along this dimension you have the nonlinear state, and along this dimension you have the linear state. So that means the particle filter will tell you how to position along this dimension, and if you then view it from this dimension, you'll see a Gaussian at each such position with some mean value and covariance. So that's the representation that's used. And the resulting algorithm, again, it's an interlinked Kalman and particle filter where all the updates are done in a not separate fashion. And the details, if you want to look at the details, which I won't talk about here, you can have a look in this paper. And that also includes results from this fighter aircraft example. As much result as we were allowed to publish, anyway. And if you want to play around with it, I've got some software online that you can try for just solving a very simple problem. But the best way to understand something is to implement it yourself, so better read the paper and implement it if you want to understand, I think. Okay, so far, just a very simple one-dimensional example. So let's, we can of course scale up and do this in 2D or 3D or XD, so let's talk a bit about that. So this brings us into the, have a look at this automotive example, where you have from, well, this was before Google Map time, I think, so it was someone else providing a map, but that's okay. So you just take that from the internet and you compute the grid of the roads, because your car will typically be on road. And then we use this road network to build up this distribution. So this is a distribution that lives on the road network. So the probability of being on road is high. The probability of being off-road is low. So the distribution, oh, you cannot see it, but okay, you can guess what it is. Just raise that out in 3D and you have it more or less. Clearly not a Gaussian distribution. So challenging to work with in a Kalman filter, for example. Again, in the particle filter, not a problem at all. You insert it. You need to think a bit about map management, of course. Actually, quite hard, but that's okay. It can be done. So I'll give you a few more examples of that. And then in terms of thinking about, so what I like to think about at the moment is this, I don't know what to call it, XD. So when you have a map that contains many different worlds, because again, what we used to think of it, because we have eyes, I look and I see you, I see this room. But if I'm another sensor, I don't just think about my eyes, but let's say I can sense the disturbances in the magnetic field, for example, which I as a human cannot do, but the magnetometer can do that easily. And looking around here, there's quite a lot of magnetic materials. So that means I should be able to move around here and build a map of the magnetic disturbances that's created by all of this metal that's present. And then I should be able to use that to position, because these are, if you look around and view the magnetic materials, they are quite irregular, hence informative or exciting, if you like. You're exciting the problem. So that's one idea that we've just started to play around with. And then you enter all sorts of interesting things. So how do you build a model of the magnetic field, for example? So that's something that we're working with. And this is just a little toy thing that we did in our lab. We just took a table and turned upside down. And on the left-hand side, you see our first little model of this, which is not the final result by no means, but it's a start. And this is something that as you can see also, it's not published yet, but hopefully it will be published. But this is stuff that we're pushing on and have some concrete ideas of how to improve this using Bayesian non-parametric models.
What do you mean by magnetic content in a table? Why would the table have any?
Yeah, good. It's probably not. Absolutely, it's probably not the best phrase. But how? Let me phrase it like this: how will your table distort the Earth's magnetic field?
Ah, okay. Essentially, because it's a steel leg.
Exactly.
Okay.
Yeah. So because if you take your compass and approach the steel leg, it's going to go crazy. But not if you have a map. Not if you have a map. Then it's going to be very, very glad to approach, because then the map will provide information. And that's my idea here.
Well, I mean, as long as the map doesn't change from one minute to the other.
Absolutely. But that's the same with all maps. That's why the Google car is driving around all the time and updating, and you have to update your GPS. But you're still very happy with your GPS. It helps you a lot when you're in a new area. But absolutely.
I can see the satellites, yeah.
Yes. No, absolutely. So as always, there are many buts and what if and so on. But I still think the fundamental idea of making use of this information, which again you might not think of because you can't see it with your eye. But if you put yourself in the situation of a magnetometer, that's all that can see. So my idea is to build a map that's multidimensional. So of course you have what your eye can see. You have what the magnetometer can see. We also have heaps of radio stuff going on here. So that I can see as well using another sensor. And then I build a map with all these things in it, and that gives you something that should be interesting in doing positioning, I think.
So I was wondering actually early on when you talked, when you picked magnetometer as one of your, it seemed like a very limited sensing capability, right? For instance, it doesn't work for your automotive, it doesn't work for your fighter plane. It might work on humans walking around, so it seems very restricted in its capability of localization.
Absolutely. But then again, for example, if you place a magnetometer in let's take an aircraft, and if you have a magnetic map of that aircraft, then you can correct for the distortions that it induces. And then it starts being possibly useful again, I think.
But a lot of the applications you talk about, GPS works. So the big one that doesn't work is indoors. And then
Yes.
this saves you indoors.
Yeah.
Extra information.
Yeah, just a little bit, but maybe that little bit of extra is all I need. So what I have in view here is exactly what you say. So this is for indoor.
In fact, if you use regular MEMS gyros for indoors, you will never detect the north magnetic pole because there is so much other distortion on the steel cabinets. Essentially, what used to be an interference, now you're taking advantage of the.
Yes, I'm making it my friend.
Right.
Or we're trying to. We'll see. But we have some initial results, and it seems promising. But then, as Maxwell told us, the magnetic field falls off pretty quickly, cubically. So that's sad.
Falls off
as in 1/R3. So that means if I'm here, then the magnetic environment here is interesting. When I'm over here, already now, I'm losing. I can't see. So that's a problem here, of course. But let's see. That's just a little ongoing thing. ID, more an ID than a result. But these are interesting as well. Okay, let's move on and have a look at some of the industrial applications. So I'm not going to talk more about the fighter aircraft. I talked about that last time, so I'll leave that. Let's do the automotive localization first. Okay, so what have you got here? So this is work together with a company called Nero Dynamics in Linköping, a spin-off from our group. They mainly do tire pressure monitoring. I could mention that as well, which is interesting. So measuring tire pressure to be able to foresee a puncture so you can stop over. And you do that without using any sensors in your wheel. You just look at the wheel speed sensors.
Sorry to interrupt. You saw where the F's and the G's come from? I mean, you saw this map where I think you said something how you can obtain a world model from this map. I was wondering, where do these models come from? In particular, the functions. So I need to see, right, to do all the computation.
Yes. Yep. So as always, no one will give it to you. So you need to figure out yourself. So how do you do that? Well, for this case, so when we have a car moving around, then I can write down the dynamical equations for a car moving around. That's a hard task, of course. But given what, again, as always, with a model or with solving any problem, try simple things first. So for this, it's enough with a very simple model, actually. So just a point mass moving around in space, and not even in 3D because it sits on ground. So, but you need to. So I haven't included any of that.
So that's deterministic dynamical model.
No, it's a probabilistic model. It's a probabilistic model. But it will, of course, still encode all the standard things that you have in. So in the car, in the Ackermann model, for example, will be in there. But then on top of that, you have the disturbances. I've shown you one simple model. Let me go back to that. Where was that? Okay, so that's one example of an F and a G. So the F here, I was just thinking, but what's happening here? Well, it's just a point mass moving around. So I'm going to model that using the equation up there. It's a very simple equation, but still it captures the dynamics here. And for the fighter aircraft, we know people have studied the dynamics of fighter aircraft fairly well, so there are differential equations that describe that motion. So we just make use of that.
So it's the V and the E here.
Yes, yes. And hence also the state, the X and the Y's, will have distributions attached to it. And for your other question, so how does the G enters? Well, that's the world model that you have. Whether that is this simple model or if it's something from Google Earth or from the 3D models from Apple or whatever, doesn't matter. But
You need to figure out the numbers, right? So when you say this is a road, this is a non-road, you need to assign probabilities to those numbers. The probability of a car being in the road or not being.
yes, possibly. These are assumptions that we need to make, which is important and hard and not obvious how to make them, absolutely. Because you can, of course, have a vehicle that has the capability of going off-road. So that means there will be a probability that it goes off-road. But we can incorporate that as well. Sure, absolutely. And that's sort of entering the art side of it, I would say, because that requires playing around with it and experience. But yeah, good question. Let's see, where were we? Okay, so the task here is to compute the position of a car, like you say. So your GPS fails, which it does every now and then. But the road will hopefully not fail. It will still be there. And you have the map with you. And you have accelerometer in your car, at least one or two. Soon, I think there will be 3D accelerometers in cars as well. Gyroscope, you have at least one for your heading. You have the wheel speeds, because the ABS system make use of them. So you have all of this on your canvas, ready for you to use. So if I use that together with a road map, what can we do? That is what we're playing around with here. So again, a very simple model of the car, more or less a point mass moving around with wheels attached to it. But some sensor models, and the world model is the PDF that we just extracted. Okay, so what happens then? Well, what can we do? Well, here's the idea. If you're driving along straight on a straight line, then I can position myself pretty well laterally, right? But not longitudinally, because my uncertainty just grows as I keep moving straight. So, and that's illustrated there. So that gives me a distribution, filtering distribution that looks like that. But if I then decide to make a right turn, that is good. That's an informative decision, because then you bring information into the system. And then all of a sudden, the distribution looks like that. And you're all of a sudden localized, much better at least. And then you possibly start traveling there, and it will start to elongate, and so on and so forth. But that's okay. At least we have, I know what the uncertainty is, because I have a representation of it. So if I am uncertain, I know. So you know some of the stuff at least. We don't know the unknown unknowns, but we know some things. No. That's true. That applies pretty well here, I think. It was said in another context, though. Okay, what is this? This is what is this? This is Linköping, a residential area close to the university where we were playing around. And took a car, attach the GPS to the car, and you have the true position, which is shown in purple, and then we insist on extracting a point estimate from the particle filter. That's what you see in light blue. And so how do you initialize? Well, we play the game that I have no idea where I am, but I have my phone with me. So that means GPS will give you a cell. So you're in this cell. I'm talking about the cell in the mobile network now. And the cell is like that. Okay, so when I use my particle filter, I have in there, I need to provide an initial distribution. So I just spread particles uniformly distributed over all the map. That's what you see. That's all these blue things. Each blue thing is a particle. The particle is actually bigger because it has velocity states in it as well. But I just visualize the position here. And then as we start moving, you can see as you do turns, as I just discussed, you gain more and more information. And when you sit here, for example, there's high probability down there, up there, and there. And then, of course, as you make more and more motion, a bit over there as well, you become more and more certain about where you are. So that's the idea. So exactly the same as I've just shown, but shown in a different context here. Let's do this indoor. So what's the task here? The task here is to compute the position of a person moving around indoors. That person has credit card-sized thing attached to it that looks like that inside, which has inertial sensors, and it has a little radio and a magnetometer. So the idea is then you're this huge company and you need to know where all your personnel are. Then you give them a card like that, and with the system that we got, you can position them within a couple of meters accuracy at least. So let me show you what happens now. So the situation, I should say, this is work with a company called Extin, also a Linköping company. And some of my students who did this work. So you have sensors reporting, accelerometers, gyro, and radio. And we have a world model that looks like this, which we get straightforwardly from the drawings, which you have drawings for this area as well. So from that you can extract a distribution which you use as your measurement model. And that basically encodes very simple model here, just encode walkable space and non-walkable space. You can't travel through walls, etc. Dynamical model, a very simple point mass moving around, and we're making use of the fact that I sort of stand still when I'm walking, or zero velocity at least. And then we use the step length to get a handle of all the uncertainty that's in these inertial sensors.
What do you use for the radio for? Is that the ultra-wideband or is that the...
No, that's not ultra-wideband. This is just Wi-Fi.
Signal strength.
Signal
So
strength.
essentially that could be your cell phone.
Signal strength. Yeah, could be.
Absolutely.
Yeah.
Yeah, you can do this on an iPhone or whatever phone. Absolutely.
The inertial sensors also, you use the ones that are in an iPhone or
No, somewhere here. I mean, similar.
So I mean, is it like an X sense?
No. No, this is cheaper stuff. It's corresponding to what you have in your iPhone. A couple of $.
Do you know the performance, Allen variance and ARW of these sensors?
Not on top of my head.
I would be interested.
Absolutely, yeah.
So you're saying it's the same grade as what's in your iPhone?
Yes.
And what grade or what manufacturer is it?
I think it's analog devices, but I'm not sure actually. That's when I work with companies, I tend not to ask too many questions. that makes life easier to work with companies. Some things are better not to know. That helps for me quite a lot actually. Okay, so let's see what happens. Let me explain. So your question, the radio, what do you... The initial idea was the following. Because in here you have a very specific radio environment. And if you want, you could map that. And that's, again, a map that you can then use to position yourself. Great idea. problem, it's expensive to build this map. Hence, we can't use it. So that's why we stopped thinking about that. But we're still using the radio to initialize. So when we start, so that's my student, and the other student is filming him as he's moving around. When you start, you stand there for a little while. So you just record the radio information, which base station can I talk to, can I see? And based on that, you can get a rough estimate of where you are. So we use that to initialize. And we're moving around in 3D, of course, because if I just hop into the stairs there and go downstairs, I'm at the other floor level. So the particle representation is in 3D in position, and you also have velocity and orientation in there. But again, to visualize, I'm only plotting a slice in 2D. So what you see here now is we're standing down here, so this is the true position. And you're initializing, you're using a radio to initialize this 3D sphere, and you're using over 1 million particles here, so quite a few. And then what's plotted here is just a 2D slice and a quarter of that, because we don't know which floor we are when we start. And as he soon he'll start moving, and the filter will start working. The same, you'll see the same thing. So here, let's pause here, for example. He's just been moving straight on. There are quite a lot of different places in the map where you can keep walking like that. So not very informative at this stage. At least some particles will hit the wall, so to speak. So they will then disappear. And so far, you see it's just the snake following there. It's just the green ones, so just the true. So we have not, at this stage, we're not certain enough to deliver a localization. Because there's high probability there. So that means how do you make a decision where you are? You can't. So rather than providing false information, we're not saying anything. Because, again, we have a handle of the uncertainty here.
So other than the initial time you used the radio, you didn't, because it's finished.
Then it's finished. Yep.
Well, I mean, a hypothetical question. If the same way as there's some effort put into generating the map, as you're generating the basic map, can't you map a lot of other things simultaneously?
Absolutely. That's an interesting question. And a natural step forward with this is to use this, because as you will see after a while here, we get the position pretty okay. So here you start obtaining an estimate of the position. And we can pause here, for example, when you're walking in this, well, maybe not that narrow corridor, but still you see what I said, the uncertainty is much bigger in the longitudinal than in the lateral, which makes sense because you're in that corridor. That means laterally you know where you are. And that means when you're entering this open area here, you would expect the uncertainty to grow laterally as well, which is exactly what happens. Because given the absolute information that we have from the map, it's not helping us here, because the map just tells you you're free to be wherever you want in this space. And then entering the corridor again, yep, the same thing happens, and so on and so forth. So it solves that problem pretty well. The computations are not ran on board this little chip. There is a DSP there, but it's not powerful enough, unfortunately. So we're just reporting the measurements to something like this that does the computations. But based on this, you can then, as you just started thinking here, well, can't you add this, can't you add that? And absolutely, we can add. That's what I want to do. I want to add more information here to get it better. Yes?
Are you going to talk at all about how you actually make that determination that, yes, we can make a point estimate now? It seems like there'd be a lot of maybe special sauce there as far as like, when does the distribution become unimodal?
Yeah, I'm not going to talk too much about that, but it's interesting and not obvious, because as you say, how do you make such a call? But a very simple way of doing it is just when is most of the probability in one mode, and make the call then. Just as a simple start for that. Yeah. Okay, we should push on. So we've now done this in air, we've done it indoors, we've done it on roads, so let's do it underwater. So the task here is to find the position and orientation of the yellow thing here. And this is worked together with another Saab company, so the underwater security. This is I've not done this work, so this is work by a colleague of mine, Richard Carlson. But since it fits the theme well, I wanted to include it. So the idea now, sort of repeating myself, of course we can use exactly the same idea. If someone provides a map of the seafloor, and we're getting more and more maps of the seafloor, even though that is the part of the Earth that we know least about. But
did Google do that already?
Absolutely, they do that, and other people do it as well, but not the entire seafloor.
Oh, okay.
But we get more and more information. But we don't, as far as I've heard, we don't know too much about what's down there actually. So what have you? Well, you have a map of the seafloor. You have your vehicle. The sensors that you got now is you got a sonar that provides you with the distance, and you have a control system that you have designed. So you know the rudder angles, so that's useful, and you have speed. So again, just incorporate that. You got the world model. We need a dynamical model for this vehicle. Again, your question in the back there. We built that, so Saab built that, so they have specifications for it and the dynamical equations, which we just make use of. And you solve the inference problem using the particle filter, and hopefully you get a good position out of that. So let's pause there for a while. So what do you see here? Well, this is just a part of Lake Vättern, which is Sweden's second largest lake, actually, close to Linköping. And this is the sea floor, so you see the height. So what have you? Here you have 8.5 meters. This is pretty flat area. Then you come to drop off 9 meters, 14 meters down here, 15 meter, etc. So you can visualize what this is. So, and then you think about this map. When given the ID we're using, that means over here, this is not good. That's not informative. That's not helping us. This is helping a lot. That's extremely informative or exciting if you talk about estimation problems. So this is the initialization. Might look strange, but given the system, you have a sonar, so you measure, you get a depth, and you just initialize particles uniformly in the map on that depth. So that's then going to look like that. And then the black curve is the ground truth. And then we start moving, and you can see as we move more and more, the distribution gets more and more focused, as you would guess. And as you move over the edge, I think you agree that that is what you would hope to happen, that you have huge uncertainty along the drop-off, but in the orthogonal to the drop-off, you know pretty well what's going on. When you're entering this area, would expect the uncertainty to grow, and it does. And you keep moving, you come to the drop-off again, the same thing happens, and yeah, you get the idea. Okay, so let's finish with a experiment which is stressful in a sense. So let me explain what I mean by that. So what is the task? Well, the aim here is to keep track of and discover vehicles that travel on road. So it's target search and track. So search for targets. You have no idea when they might come in and when they might disappear. What you do know is that they will follow the road. So that's the setting. So it's a little toy example that some of my friends in Linköping did in the lab. So let me show you. Before I'll talk you through this, but that's rather boring without seeing what the full picture is. So let's see. I'll use this to explain the setup. So this is the camera, so a gimbal. camera that sits in the ceiling. This is the map. This is our world model, so road network. These are 2 targets traveling around. Each of them, as you saw in the beginning, they have a little thing here to take away the computer vision part, so that makes computer vision very simple. So it's very easy to just detect them. This is the view, and that's the view from the camera. And when you look at that, you see that this little camera can't see much of this world. And we give it a pretty hard task. We give it the task of, you should search and you should track all objects that are moving in this world. That's going to be a bit stressful for this unit. And then, of course, that's a mechanical thing in there, so you can't move it arbitrarily. You need to respect the mechanics as well. What you see here is the algorithm's view of the world. So you see the footprint there, what the camera sees, and you'll see particles that represents our knowledge about these targets. So let's see what happens as we play. So if we pause there, you can see the camera is now looking over here, where this one is. That's what the camera sees. So after a while, after a few frames, it's simple to identify this target, and we then start tracking it. And we know that it's confined to move on the roads. So we then use a particle filter that spreads hypotheses along the road. And then when you have a decently good estimate of that target, then you should probably let that target go for a while and try and search for more, because it's not enough for you to follow one, you need to follow many. So this is what I mean by the stressful bit. So now you stop, you continue searching for the other one, and since you've found it before, you know a bit about where to look, and you look at that target for a while until you're certain enough, and you need to find the other one, and then when you're certain, you need to keep track of the other one, and so on and so forth. So this is what I mean by the stressful part. If you imagine solving this yourself, you're going to be stressed out after a while. But I think this is an interesting problem, because this widens the scope a bit. It's not just computing the position and orientation anymore. It's also making decisions. So you need to make decisions.
If your law of your particles has 2 modes now, how do you decide which one to go back to?
Then I would first revisit the one with the highest probability.
I see.
And then if I don't find it there, I'll go to the other one. Yeah.
So you assume certain speed for the dynamics of your camera as well. The
Yes.
camera can't
Can't,
be infinitely fast.
no, and it can't make arbitrary motions either due to the mechanics in there.
Sony PTZ, it's a PTZ camera, right?
Yes. And this is work by Per Skogler. If you want, you can have all the technical details are in his PhD thesis. If you want to have a look, the slides are online already. If you want to look at them, just go to my homepage. So with that move in mind, we can have a look at this. So you have a sensor platform that reports images to a computer vision module that provides detections that enters our multi-target tracker, that then provides an output, which is the tracks that are used in the planner that then schedules the sensor platform. And then you have this loop. So this is a very interesting loop, I think, where the control enters so closely with the estimation problem. So that is why I brought it in. Something I would like to do is to replace, I do some work with UAVs, to replace this with 1 or 2 UAVs solving the same task. To make it a bit more interesting. So that's something I hope to play around with. Okay, we should finish off here. So the story I'm telling, I hope I've been telling, is showed you quite a few different applications from different areas. All of them was solved using exactly the same strategy, or the underlying sensor fusion strategy, where you model the dynamics, you model the sensors, you model the world, and you solve the resulting inference problem. And we should not forget about the surrounding infrastructure, which I've only mentioned, I haven't showed you that. But issues like time synchronization and calibration and things like that is a problem here that needs to be respected and solved. There's lots of interesting research, and as you all know, I mean, the amount of sensors in the world is skyrocketing at the moment, so this stuff is going to be more and more important, I think. And I see that a lot when I talk to my friends in industry. They get more and more interested in this. So thanks a lot for listening.
In that example where the person was in your office and you used the radio as initialization and then gyro and accelerometer to localize in a map, right? How big of an area can you do that accurately? And the second part of my question is, if you had magnetic map, how well does that work?
Mm-hmm. Yeah, very good question. So let's start with part A. So how big an area can you do this in? Well, there is no direct restriction, because as long as you have a map of the area, and
I'm thinking more like a mall or a shopping center where you can't really make sharp. The map is in your example. The map is very thin. There's only certain pathways this guy could walk. But if you're in a big two-dimensional area, how well does it work there?
If you then it's a problem, because then we'll get what I showed you with this little example in the beginning.
Right. Would the magnetic thing come to your rescue in that?
It could, because if I'm walking like this, and I'm guessing that there are a bunch of magnetically interesting stuff that I'm standing on now, in terms of things in concrete and maybe some pipes and what have you.
I'm asking, in practice, are there magnetically interesting things, let's say, here or in the shopping center? I'm just not familiar as to whether that's a good enough signature for localization. How much experience have you had?
Not much yet. So for me at the moment, it's hope that the magnetic.
There's a Finnish company or something that's commercializing that, right?
The map thing, or the
magnetic localization using magnetic something.
Okay, that would be interesting to have a look at. I'm not familiar with that. So speaking about malls, I could mention there's another spin-off from our group that does indoor localization and have their system installed in 30 malls in Singapore and Malaysia.
And what things do they use? What sensors?
They use a phone.
Okay, just a smartphone.
Yeah, just a smartphone, yeah.
And do they use the radio aspect? In other words, do they need to map the mall ahead of time for Wi-Fi signatures?
No.
Or they just go in cold?
They go in, as far as I know, they go in cold. Again, it's a company, so I'm not asking all the questions there. But
what's the name of it?
Xenion Lab. Xenion Lab.
Maybe I could do it.
It's listed on the bottom of the slide there. You see a reference to it right there.
Yeah.
Yes,
Xenion.
Pair works for Xenion Lab. Yeah, good, well spotted.
Other questions? If not, thank you again. It's
Okay,
great.
thank you.